let's get started. Welcome to the session on Know Your Java. My name is Venkat Subramaniam. Thank you so much for joining. We're going to be looking at a few different common things. Mainly the things I'm going to talk about today are things that I have stubbed my toes on. And every one of these is ouch. And so I decided to share that with you so we can learn from these and talk about the do's and don'ts and what we could be thinking about. One thing I'll request you is I'm going to show you some code examples and I'll ask you what the output is. Go ahead and shout your answers and see what we can come up with. That's a lot of fun because it helps us to think about whether we are thinking in the lines of what the compiler is thinking and the runtime is thinking, or if we are thinking something different. So don't hesitate to shout out your answers. You don't have to be right. You don't have to be wrong. It just, whatever comes to our mind, right, is what these things are fun to really look at. So I'm going to take it about approximately about 6 different problems, and we're going to look at it, and then we'll talk about the behavior of the code, and then we'll talk about what we may want to think about when it comes to writing and implementing code, and how can we get the best out of the language and the capabilities. Now, one of the things that I often think about is, compilers are really great, and we all rely on compilers quite a bit. So when it comes to compilers, if a compiler were to complain that our code is not correct, we really are happy that it caught our problems, and we tend to really celebrate the compiler. But every one of the problems you're going to see here are the ones where the compiler will be happy with the code, but you may not be. And so that is not to say compilers are not useful, but it is to really emphasize that compilers are really great, but it's not sufficient to rely upon them entirely. I'm also a huge fan of unit testing. You're going to see some examples code here that are going to be incredibly hard to get tested. And you can run the code, you can write all your unit tests you want, and it will not catch the problems. Once again, unit tests are great, but you can't just go home thinking I'm awesome because my unit tests are passing. So this really comes back to knowing what we are doing, coming back to having people review the code, thinking through the code, the semantics and the behavior. So that's one of the challenges we have to often work with. So with that said, let's get started with our very first example in here and see what this has for us. So here is the first code example I want to start with. Not a lot of code, as you can see here. We created an array list using a new array list, and of course initialized it with the list of values 1, 2, 3. And I'm going to print out what the value of the list is. And I'm expecting it to be 1, 2, 3, obviously. And then I call a remove on 1. And then when we are done with it, I'm printing the numbers again. And in this case, the output is going to be 1 and 3. Let's verify it actually is. So when I run the code, you can see the value is 1, 2, 3, and the output again is 1, 3. So that's exactly what you saw in here. So the code is doing exactly what the comment says the output will be, the 1, 2, 3, and 1, 3, as we can see. However, my question here is, I'm going to modify this word list to a collection like so. So I'm going to take this list, and instead of the list, I'm going to change it to a collection. Now, as you can see in this particular case, we have, of course, you can see that when I have the list, it's a 1, 2, 3, and 1, 3. But when I change it to collection, what do you think is going to be the output on this line of code? Anyone wants to try? A 2, 3. And others probably are still wondering, and that's perfectly fine, right? So this is the catch over here. When you run it, it's 2, 3. So what in the world just happened? So let's think about it. And this is also a lesson for us to think about when it comes to designing our own APIs, our own libraries. As it turns out, the collection has a remove function method, and so does list, which has a remove method as well. So in the remove method of the collection, so when you go back to the code we had a few minutes ago, if you notice when you run this code, it got rid of the 2. And the reason, of course, is the index right here is index 1. So it turns out that we have a function right here which is going to take an index. But as it turns out, the collection has a function that takes an object, and so does the list. So far, so good. But then what they did is they overloaded while overriding a method that takes an int. This technique is also known as bad idea. So essentially, when you do this way, when you override and overload it, what happens is, in this particular case, there's a bit of an edge case. So essentially, when you passed an integer, well, it was doing an auto boxing into an integer object. But on the other hand, when it's a list interface, it took the direct integer directly and used it, and so there's a confusion. If you dig a little deeper into this, this goes back to Liskov's substitution, if you will. So substitution principle, so this is something to think about in a sense is, what a long word, isn't it? Substitution. Okay, so I'll try this again. Principle, basically, and the idea really is that you want to make sure that you don't have surprises when you override. And in this case, of course, it could be surprising depending on how you use this object. So something for us to think about. Now, this is a problem with the way we have overloading and overriding. But having said that, things can become a little bit more surprising, if you will. Suppose you had a piece of code like this, and when you run the code, obviously, you see a value of 1, 2, 3, and 2, 3, so that's all great. And then somebody like me comes along who is really, really excited about a type inference. And so I want to change this to a var. Now what's going to happen? Well, as it turns out, a second ago when I had a collection in here, you notice that the output is 2 and 3. But if I use a type inference, on the other hand, the output is a 1 and 3. Well, the reason for that is when you use a type inference, the compiler uses the information it knows, and in this case, only thing it knows is that this is an array list. So the numbers right now is a reference of type array list, not a reference of collection. So again, it ends up picking the wrong one. So the moral of the story is, it's a great idea to verify what the code does when you actually write the code. So again, testing and making sure that it's consistent with the output we expect is generally a good idea, and that is what this emphasizes. So something to really think about when it comes to that. So moving a little further with this is the next ouch I want to talk about, and I still have my pinky in pain because of this stubbing that I had with the code. And so here is an array list I'm creating. So I'm creating a list equal to numbers is equal to arrays.asList. And once I create an arrays.asList 1, 2, and 3, you can see that I'm printing out the value of this list, and obviously it's 1, 2, and 3. But the question is, I'm going to perform an add operation on the list, and if it was successful, I print added. If it was not successful, I say unsupported. Similarly, I call a set method on this at position 2 and set the value of 2. If it was successful, I print set. Otherwise, I print unsupported. So that's basically what you're seeing. So what do you think is going to be the output for this part and this part below? Any tries? So unsupported for the first one, you say. What about the second one? So when you run the code, it says unsupported, and it says set, and gives you a value of 1, 2, and 2. So a lot of us may have tried add, and it failed. And if you're like me, you walked away thinking that array list created by the as list is immutable. And this is unfortunate because I came to know it is not, but when somebody else pointed out, I'm like, really? And that's really annoying when you figure this out, but that's exactly what happened in this particular case. So the answer here is, when you call the add function, the add was not supported, so it blew up with an exception. But when you call the set function, it did modify the collection at that location. So as a result, it is not an immutable collection. So what's the moral of the story? My recommendation is, this was great back in Java 5. And as list was introduced in Java 5, and I'm sure a lot of us have used as list in our code as much as I've done as well. But I highly recommend to retire that function. Moving forward, I sincerely recommend that we use the list of function. That is a much better alternative, a replacement. And the reason for that is the object created by list of is actually immutable. So when you notice the code now, when you run it, it says unsupported and unsupported, which is what you really want. But just to emphasize this a little bit more, if you ask for the numbers.get class, if you will, that clearly communicates to you saying it's an immutable collection, so that's really a nice thing to do. So if you're writing code using functional programming, or if you really want to create code with a fewer errors in it, and if you really want to honor immutability, that can be really a nice way to do. So a list of, set of, and map of are all good functions to use. And of course, immutability is great for some number of reasons. When something is immutable, you can share it very safely. But not only that, when something is immutable, you can make a copy of it safely as well. So you can pretty much rely on it very much. So that's one of the reasons why immutability is really useful to have. And of course, if you're going to rely on immutability, you want all the help you can get in terms of APIs that will create immutable classes and immutable objects rather, and this gives you that ability as you can see in here. So the recommendation is, and again, I'm not suggesting you just go out on Monday and start looking for all the code to change, but if you're going to modify a piece of code, and if you come along as list, make a note of it and modify it to a list of as you move forward and upgrade to newer versions of Java. List of was introduced, of course, in Java 9, so if you are beyond Java 9, you should be able to make use of it readily and right away, so that is something I would highly recommend that we do compared to using as list. So I'm hoping that eventually maybe as list may be deprecated so we can move towards something much better in the long run. All right, so far so good. But the next one is ouch, but I want to tell you a situation before I tell you that ouch. So this was an email I got from a developer. And his email started by these words. He said, Venkat, here is a piece of code that worked fine until yesterday. And it doesn't work as of this morning. What am I doing wrong? Well, this person works for, I'm not going to say the company name here, obviously, but he works for the company that has your money. Let me just put it that way. And he was working with a bunch of hedge funds. And I didn't have to look through the code a lot. I glanced at the code, and immediately my response was, oops, we shouldn't be doing this. Well, obviously, I don't want to show you a complex code here with hedge funds and all those maps and filters and reduce, but I decided to distill that to something really, really simple. So here is a piece of code where we have a names, which is a collection of names, as you can see. And I have in uppercase, which is a new array list I've created right in here. So now within this code, I have a stream that I've created. And within the stream, I have created a to uppercase as a mapping. And then, of course, in the for each, I take the name that's been converted to uppercase and I put it into the collection in here. So when we are done, I print the size of the collection that was the original and the size of the result collection. Now, you might really know that one of the properties of the map function is that it preserves the cardinality. So if you have an n number of elements coming in, you will have n number of elements after the map as well. So that is expected. So if I run the code right now, you can see it says 7 and 7, so that you can say the code worked. But here's my question, what is wrong with this code? Any tries? Maybe we can play the Jeopardy music. What do you think is the issue with this code? What was that again? Will the size be 8? I hope not. That would be more elements than we have. So, first thing you may say is, it works. And my recommendation is, do not say, I would recommend. So don't say, I would say, it works. It's okay to say, it behaves. That's what I say these days about code. I don't say the code works. I say it behaves. Sometimes it's like the rude puppy that you have in the house. You have no clue what it's going to do. So you look at this code, it looks very innocent. In fact, it's a little bit more troublesome. When I go to companies and I look at some really horrible code, or when I look at a code that's really misbehaving, I would turn to their lead developer and ask the question, why did you write it like this? And consistently, here's the answer I get from the lead developers. Venkat, you should know, this code was written before I joined the company, right? So this is the consistent answer I get all the time, right? So it's very possible the person who wrote this code is long gone, and you, the new hire, also known as the victim, inherits this code, right? And then your boss comes to you and says, we need to improve performance. And you're like, boss, no problem, I got this. And you make one small change, right? And what's a change you make? You simply say parallel stream, and then you're like, cool, I'm making this faster. And then 3 weeks later, you get a call from your support team. It's like completely messed up. Some clients lost their data. What are you doing? And you're like debugging right now. That's no fun, isn't it? So I ran the code, and guess what? It produced 7 and 7. You can write all the unit tests in the world you want. You will not find this problem. You need to know this code is messed up. If you don't know, you're going to know it in a very hard way, right? So what's the problem with this code, you may think? Let's go to the command prompt for a second, compile this code for a second. Now let's run Java sample and just run that code. 7 and 7, isn't it? But let's see, well, let me put it this way before I go further into it, before I say this. So I'm going to say, I'm going to say, let's go back to the code for a second, that if you are very lucky, the code will fail on your machine, right? If you are not lucky, you know the rest of the story, right? It's going to fail in production. This is one of the biggest challenges you're going to run into with code like this, unfortunately. So if I go back to this code, and if I say Java sample, and you can say, hey, it produced the result, isn't it? But I'm going to go back to this code, and I'm going to run this a few times here. Let's just see what's going to happen. It's full of surprises, isn't it? That's why I keep exclamations on it. So yeah, it seems to be not producing any values. Did you notice that? Right? So this is called being lucky. This is called not being so lucky. So I have seen values like 6, values like 5. Maybe that's a good random number generator, right? But that's not going to be fun at all. So you have no clue what there you can see a 6 right in the middle someplace, nothing in this run, and there's a 6 here as well, and another 6 here as well, and you have no clue when you may see a value of 5, for example. I've seen that as well. So it's incredibly difficult to prove that correctness of that code unless you know what's happening. So what is the problem? I think we all will agree to this following fact, isn't it? So the first thing, wait a minute, don't take photo yet, please wait. Don't do this. Now take a photo, right? So, people take photo, put it on Twitter, and somebody says, this guy is stupid, right? So now take a photo and post it. So don't do this. So the problem in this case is, the real concern with this code is this. You could say, generally speaking, mutability is okay. We all have done that, right? So mutability is okay. But what about sharing? Sharing is noble, right? So you want to share. Remember what mom told us. You need to share. That's a good idea. But shared mutability is devil's work. So this is what really happened here, is we have a shared mutability. So how do we have a shared mutability in this case? We have this piece of code that is performing a mutability right here, but that mutability is to a variable that's outside the pipeline. So imagine, I'll give you a crude equivalent of this, and I hope you will never try this, I warn you. Imagine being in the pipeline is like being in a train. Now, you all know never to put your hands out of the train when it's running. That's what this code is doing. It's putting its hands out, it's putting its feet out. You don't know what's going to be missing. That's exactly what happened in this case, right? So it's a shared mutability. So when multiple threads are running, those threads are talking to a shared variable. Now, somebody asked me the other day, hey, I can fix the problem, he said. And I said, how do you fix the problem? He said, I will make this into a concurrent list. Now, that particular approach in software development is called hope. That's a good thing to have, right? But the problem really is that completely defeats the purpose of doing this, right? Because now you are saying, look at this power of multi-threading, I don't want it. I'm going to slow them all down and I'm going to make it serialized. Now you got more debugging to do as well. And the minute you start synchronizing, you never start smiling after that, right? Because every time you synchronize, it becomes harder to maintain it. Why bother? So the moral of the story is, in fact, this is a great example of what is called less is more. So what you really want to do here is to simply go back to this code and say, no, I'm not going to do that. I'm going to simply call the to list over here and be done. And now you have guarantee of thread safety. In fact, you put less effort right now than you did a minute ago, and you leave it to the people who know better to handle this than we trying to fix it. So this is actually thread safe, and you can parallelize it all you want, and that's going to work as well. So the moral of the story is, do not perform any shared immutability from within a pipeline. That is a disaster waiting to happen. It's literally a ticking time bomb. It's going to blow up one day. And when it blows up, here is the irony of it. You'll call your colleague and say, look, it failed. And they will tell you, run it again, let me take a look at it. And you run it again, and there's no taking a look at it again, right? It's extremely painful, so it's important to avoid these things. The only time I recommend you write the code I wrote is if you really hate the people you work with. And do that before you quit and walk away as the building burns down. Otherwise, don't do it. It's not a good programming practice. So with that said, let's go to the next one here and take a look at one more example in here. So this code example here that we're going to be looking at right now, let's take a look at this here. So this one, I'm going to blow away the sample.class. I don't think we need it. Let's go back to the sample.java in here. So notice what we are doing in this particular code. And I need your answer for this one, but let's read the code before you give the answer. So in this code, I have a factor, which is an array of values, in this case, the value 2, as you can see. And I have numbers 1, 2, 3, and I have a stream, and within the stream, I'm saying map and number times factor. Then I say factor equal to 0, and I'm going to output the value. So the question to you is one of 3 choices for you. First choice, the result is 0, 0, 0. The second is 1, 2, 3. And the third is, I have no clue, I want to go home. So what is your answer? Some people are saying zeros. Anybody else? You have no clue is the right answer. I love it. I like to ask this question in the interview, by the way. I will give this question. If they attempt to answer, they are fired already. The reason is, I don't want people to be creating Java puzzlers. I want them to create production code that can be maintained. If somebody writes this and feels proud, walk them out of the building, right? Because you want them to write reliable code. The reason this is really a treacherous path is we need to really understand the semantics of the code in here. In all fairness, let's take a look at this really quickly, but with a slightly different example here, if you will. So I'm going to take an example in Kotlin just for a minute. So I'm going to say numbers equal to, let's say, list of 1, 2, 3 for a minute. And I'm going to say, let's say val result1 equal to numbers, let's say numbers.map. Let's say in this case, I'm going to say given a number, I want to simply return in here, let's say a number. I want to return a number, let's say times factor. So let's start with that. Then the next thing I want to do is to go to result1.forEach, and I want to simply take the number again, and I want to simply print the number like so. So a very simple example, as you can see here, and I'm going to say factor equal to, let's say 2, and we start with that little example here. So when I run this code, you can see in this case the result is 2, 4, and a 6, which is what we expect, no surprises over there. However, if I go back to this code here, and if I say a factor equal to 0, what is going to be the result of this execution? 2, 4, 6 or 0, 0, 0? Look at that confidence that came right there as 0, 0, 0, right? I love that confidence. So what just happened? This is the reason why that good answer is no clue, can I go home now, right? So that's usually a very safe answer. As it turns out, in the case of Java, the execution is always lazy. In the case of JavaScript, no, never mind. So in the case of Java, the execution is always lazy. In some languages, it's always eager. In the case of Kotlin, you get to choose. So you can say as sequence over here in this case, and if you run this code, you can see the result is a 0, 0, 0 because that's a lazy evaluation. However, if you don't have an as sequence, the result in this case is a 2, 4, and a 6. So it really comes back to the question, is it an eager evaluation or is it a lazy evaluation? As it turns out, originally you were right, it's a 0, 0, 0, but that's because Java has lazy evaluation all the time. But if you're programming in multiple languages, imagine your life dealing with this. Because every time you look at this code, you got to stare at it and remember and think about the language and the semantics. But the easiest way to fix it is not to do this. And the reason for this failure is that the function is not a pure function. And that is exactly the point, is the above function, the lambda that is not a pure function. So why is that not a pure function? Let's define what pure function is. And sometimes people are surprised at this definition of pure function, but it's really important. I'm going to say rule 1 is necessary, but not sufficient. So here is my definition of what a pure function is. Well, you can say a pure function is idempotent, it doesn't have side effects, but here's my definition. 1, I would say a pure function does not modify anything, does not cause side effects. So I think we can all agree to that. And you're probably going to say, duh, it's obvious. If a function is pure, it shouldn't mutate anything. Well, I agree, but that's not enough. There is something else we need to keep in mind, and that is a pure function does not depend on anything that may possibly change. So this is important for the rule of purity as well. If you don't think of the second rule, we're going to get in trouble. Because when you look at the function here, what did it do? Clearly, it did not violate rule number 1. It did not mutate anything. However, it is violating rule number 2 because it's depending on something that may possibly change. So on one hand, this code is very error prone. On the second problem, this code is incredibly hard to reason. And third, you are going to be changing this code, and you may run it parallel, you may run it lazy, and you have bugs in the code. This becomes very expensive to maintain. So when it comes to the functional pipeline, it's very important for us to preserve the purity of the functions. And if we don't, it's going to be really, really hard to maintain that code. And this kind of goes back to the previous example we saw, where we're trying to modify that collection from the outside. But looking at this, you may say, yeah, but I'm not modifying the collection, right? I'm just only using the value from the outside. So this is both ways. If you mess it is problem. If somebody else messes with it, that's your problem too. So you need to make sure that you have purity roundabout. That is something you got to be very careful about. So hopefully that gives you an idea about how we can get into trouble with this. So the answer to this question is, what do we do in cases like this? Well, it's really important for us to rethink about how we design code with functional pipelines. So in general, though, when you build a functional pipeline, try to build it with the purity so that while the pipeline is executing, you don't have the risk of either modifying some data, and you don't have a risk of looking at data that possibly is being modified outside while the pipeline is running. So in this case, you can build the core of your system to have pure functions where the functions don't really depend on anything mutable and don't really mutate anything. And then on the peripheral, you can design the application in a way that you can take an output from a database or a remote service or wherever, and then you can send an immutable copy through your pipeline, do the processing, do the transformation of data, and when you receive the data on the other side, you can then perform your mutability and make sure that the pipeline is still safe in terms of the purity of the functions. So it takes a little bit more caution. This is one of the problems you often have to deal with. If you're programming in a language like Haskell, Haskell is a very highly opinionated language. Haskell will not tell you you should make things pure. It will tell you you should make things pure, but it'll also follow you home. It'll sit and be staring at you, and you're having dinner, and it says, no, I don't want you to be thinking like that, right? So it's a language that enforces purity all the way through. But Java is a hybrid language. It allows mutability because that's been the tradition of the Java language, and functional style has been bolted on top of it. And as a result, it is our responsibility that we honor purity because the language is not capable of doing it, meaning the compiler cannot guarantee that in every aspect because the compiler can be used in different contexts, so they cannot really verify that, but it's our responsibility. This is, again, really comes back to one word, which is called discipline. So we need to really have the discipline. If we don't have the discipline, this is like slinging a saw across the room, right? Very dangerous. You know what you're going to chop off. So you got to be very careful. Very powerful tool, but we got to be responsible using the tool as well. That's very important. So with that said, let's go to one other example right here and take a look at the next example in here. So this one is going to be a problem where I have a list, as you can see in here. And the list dot stream, I'm going to first of all just go ahead and execute the stream right here. So when I run the code, you can see it's saying transform main, and then print is in main, transform is in main, print is in main. So everything here is running in the main thread, so there is no surprise over here. Now, on the other hand, I'm going to go back here and change it to a parallel stream. So when I make it a parallel stream, what is going to happen right now? So when I execute this code as a parallel stream, notice in this case, the transform starts with the main, but then the next transform is in fork join pool, and the print is in fork join pool. The transform is in fork join pool as well. So we know something from this piece of code. We know that this is running in a parallel stream, and this is running in parallel stream as well. So, or we can say fork join pool and fork join pool as well. So that's great so far. We got full parallelism on it. And of course, if I were to change this to a stream again, this is going to be in the main thread, and this is going to be in the main thread as well. And that's basically what we are seeing. But the question now is, what if I were to go back to this code, but I'm going to say dot parallel right here, because I really assume for a minute that this transform function is time consuming, and I really want them to be run in parallel. But then I realized, well, that's great, but I really want to print the data sequentially. I don't want to be printing them in parallel, so I'm going to say sequential. So now the question to you is, what thread is going to run this code, and what thread is going to run that code? Second one is sequential, you said? Is that what I heard? Any other thoughts? What was that? What was that response? Oh, I did that. Well, in this case, the response is, why me, right? So, yeah, but that's a good response too. So, what's happening in this case? When you run the code, the entire pipeline is in the main. So the whole thing is sequential. So this is something we got to be a bit careful about. Once again, we need to take the time to understand the semantics of what we do. So back in this code, let's say we are starting with the stream like you see up here. So somebody gives you a stream, let's say, And you take the stream and you perform a map operation, a filter operation, and then you still have a stream and you send it to somebody else. They receive a stream. And if I ask you, is your stream running in parallel or sequential? Your honest answer is, I have no clue. Why? Because you don't get to decide that. It is somebody who decides it anywhere until the terminal operation is executed. So in this example, as you can see the map sitting here, and I'm going to just add a couple of more maps just to illustrate the point. You can see all of them are in the main, as you can see. But in the very end, I say parallel like so. And when I add this parallel, the entire stream is in parallel. And the reason really is, here's a way to understand this. Don't think of this as a positional command or action. Think of it as a coloring or a favoring what the entire pipeline really is. So you are telling, if you want to think about this, change the threading on the entire pipeline. That's what it's really doing, right? So you're changing the threading on the entire pipeline. So if you were to say parallel, you are setting the streams threading into parallel. So the entire thing, as you can see here, is running in parallel, as you can see. Now you may be a little surprised to see the main over there. The reason the main exists over there is, let me talk about that before we go into this. So let me quickly go back to this main for a minute. And in the main, let's just not call this, let's talk about that real quick before we go any further with this. So if I go back here and say output, let's say a runtime, .get runtime, and in the runtime, I'm going to say, in this case, a dot available processors. So notice that in this case, you will notice it says 16. However, if you create the threads and look at the parallelism, you will notice it only creates 15 threads, not 16. The reason it creates 15 and not 16 on this machine is that when you create a fork join pool, it contains n-1 threads, but that one thread is the main. So the main participates in that pool as well, being the external member. This is done very cautiously. The reason is, if you're doing computation-intensive jobs, you should not have more threads than the number of cores. If you create more threads than the number of cores, you may start trashing your application. So the designers were very careful in deciding that the common pool will have one thread less than the number of cores, and the main participates in it as well. So when you see the main in this particular output, don't assume it is sequential or single-threaded. Those mains are actually going to participate in the thread if there is a thread that is involved in that case. Now, so when I put a parallel right here, as you can see, you notice that it is going to run all in parallel, but notice that transforms are called from the parallel thread. That's what you're seeing. However, if I move this parallel up here and add a few more of the map, both the maps before and after run in parallel. So this parallel is affecting that part, and it's affecting this part as well. However, if you were to give somebody a stream and they take your stream and before the terminal operation they call sequential, then this parallel is really useless. So this is kind of thrown away, and the whole thing is really running in a sequential operation. So the moral of the story is, you don't have segmentations in a pipeline. Your pipeline is entirely a sequential execution or entirely a parallel. There is no segmentation in it. However, don't assume that's the case all the time. This is where, when you look at a piece of code, you got to be very suspicious. You cannot look at it and assume what it's doing. The same code, by the way, if you're writing in Reactive Stream API, the behavior may be different. And I say maybe in this case, because in Reactive Stream, if you use an observable versus a different API, you can modify whether it's segmented or not. And so there are differences you can really have in Reactive Stream API, some segment that's asynchronous, some that is synchronous, and some other segment that's synchronous, and you can go back and forth with it. So you need to really take the time to understand the semantics. And if you don't, you're going to be in surprise. And that is something for us to keep in mind. So we looked at some of the streams and all those good stuff. But let's get back to something a little bit more fundamental that we have seen many times, but it's easier for us to miss. So here's a class called base, and the base class contains a constructor which calls check, and the check method doesn't do anything right now. Then you have a derived class where you have a string. The derived constructor sets the string's value to this dot value. The check function in the derived says, if the value dot length is 0, then throw runtime exception, value is empty, and tells us the value is actually empty. So that's the code we have so far. So the base has a constructor and a check, the derived has a constructor and a check, and the check function of the derived checks to make sure that the string is not empty. So then in the main, I'm creating an object of derived. And once I create an object of derived, I get the exception and I print the exception. The question is, this is the only line that is outputting in this particular code. So the question really is, what's going to be the output of this line of code? What was that? Null pointer exception. Woo. Who would have thought of that, right? Null pointer exception. Who here likes getting null pointer exception? No, one person, right? Well, it's horrible, isn't it, when that happens? And this actually, I'm not kidding here, I'm not exaggerating. This is a true story. My good friend Brian Sletton was speaking in a conference, and he decided to relax a little bit. He went back to his hotel room, and he turned on his TV. And literally, the TV displayed a null pointer exception. I'm like, no need for horror movies anymore, right? This is good enough. You turn on the TV and you freak out. And clearly, somebody did not handle the exception. And you know why, right? Because they put an empty catch block and somebody said, we don't do it. So they said, throw from that, right? And end of story. Or maybe they casted that to a runtime exception through it, right? I don't know. But the point really is, that can be really scary. But the question here is, what's the result of this code? And you are absolutely right. It was a null pointer exception. So the question is, why did we end up with a null pointer exception in this particular case? The reason really in here is, we are doing something that is morally wrong. And this is something we need to really keep in mind. So when you call the constructor of derived, the constructor of derived is not called first. The constructor of base is called first. So if I go back here to this code for a minute, and if I say over here something along the lines of output base, let's say constructor called, and I'm then going to say in the derived constructor, I'm going to say in here, let's simply say derived constructor called. So let's go ahead and output that right here, and we will say this is going to be the deriveds. So let's say this is derived constructor called. So let's go ahead and print that out. So when I run the code, notice it says base constructor called, and it blew up with an exception. It never said derived constructor called. What is the reason for it? Now if I go back to this code, and in here, if I print out, let's say over here, we'll say check called right here. So when I say check called, and I'm going to remove this offending code for a minute, and if I run the code, notice the base constructor called, check was called, then the derived constructor was called. So essentially what's happening in this case? What's happening here is, this is polymorphic, right? So this is polymorphic. So essentially, it's a virtual method. So the runtime says, hey, what are you doing? I want to create an object of derived, but that's an extension from the base class. No problem, call the base constructor first, then call the derived constructor. So you can see the base constructor, then the derived constructor is running. But when the base constructor is called, the runtime says, oh dear, that is a virtual function. Remember what a virtual function is. The function that is called is not based on the compile time type, but the runtime type of the instance. So what is the runtime type of the instance at the moment? Why it is a derived that we are creating. So it says, oh, so then call the derived in the check in the derived class. So it comes over here and executes the check as the second call. Once derived check finishes, then it goes up to run the constructor of the base, of the derived, and you can see that is executing as well. But unfortunately though, when we call that check, the constructor of the derived has not been called yet. So as a result, the value is null at the moment. It has not had an opportunity to initialize, and that's the reason why it blew up with a null pointer exception. So what's the moral of the story? So the moral of the story is, do not do anything. Actually, that's a good stopping point in itself, right? But do not do anything useful in the constructor. Or rather than saying useful, I should say anything, maybe I should say significant in the constructor. So this is one of the tenets we need to follow when we write the constructor. The constructor's job should be simply to initialize variables and walk away. If you are doing any work in the constructor, that is a dangerous situation to be in. Because if you're doing something significant, you got to worry about its execution, its failure. Then you are dealing with exception from the constructors, which is a terrible thing to do as well. What if the code you're calling starts other threads in your application? I know this becomes very scary. So this is one of the reasons why in effective Java, they really recommended that we actually write a separate factory method and don't really use the constructor to create object. So what you could have done is, you could have said, I have a static method, I'm going to call the constructor to initialize the state, and then call the method to check. That would have been very safe, because then you don't have this problem of a derived method being called before the invocation of the constructor. That's exactly the point. You have to be careful. The problem in this case is, before the constructor of the derived was called, the check method was actually called, which I would think you would agree is a breach of invariance. Because one of the invariants you need to honor is that a function in an object is never called before it's fully constructed. So this is breaching the invariant by calling a method on the object before the constructor is executed, and that's really, really a terrible thing to do. So that is something we have to be very careful about when it comes to how we design the code. And again, to really emphasize, there is no point in complaining here, maybe Java did something wrong, because there is no really good answer in this particular example. If this function were to be called on the base class, you are in trouble as well. And if this function is called in the derived class, you're in trouble as well. This is truly an example where you are doomed either way. So the best thing is to really avoid it, because there is clearly no good solution in this particular case. So to summarize what we talked about here, we looked at a few examples, but these examples are, like I said, things that I've stumbled upon, stubbed my toes on it, or I've seen other people stub their toes on it, and I was just around to sympathize with it. But the point really is, we need to be extremely careful to understand the semantics of the code. We need to really deeply understand the behavior of the code, and if we don't, we may create application code that actually behaves in a way that we don't understand, that increases the cost of development, cost of maintenance, so we have to be really careful about it. Definitely compilers are awesome, but don't put all your faith into that one basket. Clearly, unit testing is amazing, I love it, but I'm not going to walk away thinking everything is great because my unit tests are running. We definitely need to take the time to understand. Use tools that may look at the quality of your code. Rely upon your colleagues to review the code, and collectively we can make sure that we understand the code and reduce the errors over time, and we can make the systems much better. I hope this was really useful. Thanks for joining.